sick. So, yeah, I don't think so. All right, so hop on here. No, those I try to select as many as possible.
Because they're really nice, especially if you don't really know a step. Like you could skip it and you could figure out how it happened.
So then, should I keep it purely for tutorials?
I guess you can rip off the question.
Maybe assign the tutorials, and then.
Yeah, that actually
Try that.
tutorials. That would be great.
Because if you have, because like even like at least for certain problems, I know like there's one point I just didn't know what to do and I used the tutorial and you could skip like it goes part by part and you can skip so you could so that's the point with that, so that's how that happened. I know that helped me a lot.
All right, that's an interesting strategy. I think I might do. No, I know, but the whole point is that if I just assign the tutorials for all my students, it might actually help a lot.
Try testing it and see what happens.
Yeah.
Work out, just drop it.
All right, so let's go straight to the potential. All right, so electrical potential energy. A proton and electron are in a constant electric field created by opposite charged plates. Of course, what is that called? That's a capacitor. You release a proton from the positive side and an electron from the negative side. Which feels the larger electric force? Wait. Wait. No, it has to. This is obvious.
It doesn't even matter where it is.
The answer is?
Same.
Yeah, same. Yeah. Okay. Now we go to actually a real question. Which has larger acceleration?
Would be the one with the electron.
Electron. All right.
That's what I think the last time, and I'm like, wait, that's
So now we go to the real question. Which one has more kinetic energy?
Oh, true.
It's equidistant from the plates, right?
Yeah, so photons.
Yeah, they're equidistant from the plates.
No, it'd be the electron.
Yeah, because velocity is squared.
Yeah, but this will work energy.
That's right.
If you have the same change of potential.
That's right. Since your potential energy is U, and your U is going to be the same, it's QV. The V is the same for both, the Q is the same for both, the U is the same for both. Since the U is the same for both, then the KE is going to be the same for both. Does everybody follow this? Everybody follow the logic?
Can you repeat that one more time?
So, U equals QV. V is the same for both. Q is the same for both. U is the same for both. Right? Change in U equals a change in KE. They're both starting from rest. There you have it. They're both equidistant. Kinetic energy is going to be the same. Perfect. Troll question. All right. Which group of charges took more work to bring together from a very large initial distance?
Oh, that's a sick question. Get some paper. Let's get some paper. Right. Yeah, first one has first charging, and the second one's two. So it's like three. And that one's gonna be just two. Two, the one number two is three. No, it's two. That's K.
All right. So what do we got? What do you guys think? You think 2?
2.
Why?
Well, because if you do like, isn't it like K like Q, and I guess it's screwed Q, that's like an extra charge that has.
Okay.
Wait, no, wouldn't it? No.
So let's actually do this. To bring 1 a distance d away from 2, what would you need to do? What would it be? It would be 2 times 1 over d. Who cares about the k? So we have 2 times 1 over d. Scenario 1 is 2 times 1 over d. But scenario 2, what do you have? Let's first remove both of these. Takes nothing to bring this guy here. So then we bring this guy in. How much does it take? 1 over d. Okay? Now, let's bring the third guy in. To bring him into here, right, for this one, this interaction is going to be 1 over d. And the other one is going to be 1 over d. So this is going to be 3 times 1 over d, which is equal to 3 over d. And so 2 is greater. I think I have another way of, yeah.
Just for that, so you'd have to do, so for the first 1 times 1 over d would be to get one of them.
To pull in the second one.
Okay.
So first you remove both. It takes nothing to put this one there.
Yeah.
Then you only remove this one. You figure out what the interaction is between these
So
two,
that's your first one.
right? And then this one is going to be interacting with both of these.
Right, so you have to do both.
Yeah. So, all right. What is the electric potential at A?
Wait, is that 3060
Is there a time? Oh, so Q. So
Yeah.
the
You can come in and look at it.
is 50.
Yeah, this is 3069 trying before A.
Because you can see the
60 30. 60 30 52.
60. What? What did you just say?
60 32.
the length.
60, 30, 52. What is that?
The lengths of the triangle. Well,
Yeah, but
the 52 is supposed to be estimated, but
oh, that's root 3 over 2. Got it. All right. What's the electric potential at A? Well,
This is gonna be half. It's okay if you feel that you are.
which means it's going to be greater than 0 or less than 0? It's greater than 0. Why? Because it's closer to the positive charge, period. All right, and B, it's going to be? It's right in between. So it's equidistant.
No answers were configured for this question.
Huh?
Yeah, it says
No
this.
answers were configured for this question.
Ah, you lose. So take a look.
I do, but I just used them, so I don't think you want.
My God. Looks like he's sitting on the benches today.
No, I got some. I sit on the benches.
Oh yeah, you're out of soccer.
Oh, nice. All right. So what's the potential at the origin of the XY axis? In other words, what's the right at the center? It's going to be 0.
As long as they're equidistant.
In other words, all along that y-axis, it's going to be 0.
Well, if they're both positive or both negative.
If they're both positive, then it would be double the. It would be double. Well, not necessarily. It would be double the potential just from one of them. So, 4-point charges are arranged at the corners of a square. Find the electric field E and the potential at the center. And so I guess the point of this problem is to show you that the field and the potential not the same thing.
Yeah, field's gonna be that way, potential's gonna be 0. Yeah, because it's the same difference.
Potential would be
Now that sounds like the cold I have.
You're rough and dirty.
Hey man, it's all part of the plan. Oh, I just found out something great from Mr. Quinn. Turns out I let you guys out Mr. Quinn. I've been letting you guys out 5 minutes early for over a year now.
What?
For what?
For lab.
Really?
What?
No! Lab ends officially it ends at 11:07.
Oh, 7? Really? That's so late.
No, I barely had it.
So I'm going to be nice and let you guys out at 11:05.
You left on 11:05 anyway. I looked at the clock. I'm like, it's 11:03. Get me out of here.
So what do you guys have here?
I mean, we can't answer.
Oh, you should be able to answer.
No, it's not letting us.
Really?
It's just on this. No answers.
That's strange. Give me 1 second.
No choices for this one. No choices.
Oh, I guess I don't know what happened. I can always modify it later. So the answer clearly is 4. Why? The electric field from these two charges is in what direction? That way. Electric field from these two charges is that way. So, but the potential is definitely 0.
And the only reason is because the potential is not that clear. It's just a number.
Correct. But now there is going to be, there are consequences to this. So the fact that the electric field is non-zero and the potential is 0 there tells you what? What does that tell you? Well, if E equals dV/dr, right? Now, no, it doesn't tell you much. Doesn't tell you much. I was thinking the other way around. Huh?
Because you would get negative, you'd get negative potentials.
Well, I think it does tell you something. I think it tells you that it's an.
At this moment, there's no potential, but right as it moves outward, it makes sense. It's
You
gonna
have
be
negative potential.
I think what this tells you is that it's an unstable. It's an unstable configuration, because if you just tap it a little bit one way or another.
Well, even if you just
No, actually, even if you let it go, it's still. No, I don't think you get anything from this. All right, equipotential surfaces. So this is what your lab's going to be about tomorrow. Equipotential surfaces. By the way, have you guys started any of the potential questions for the free response questions?
Assignments yesterday, today's the response.
Okay, so finish all the free response questions except for the ones that involve conductors.
Yeah. I was trying to do this one again.
Just quickly, I'm taking the physics SAT too.
When? Have you been like progressively studying throughout? Good.
Oh, the subject test?
Yeah.
But I'm not stupid.
Is it really?
It's gonna be wrong.
It's really easy, but it's just a lot of material.
Yeah, I had to remember. I mean, I like didn't even have time to like learn optics and stuff. So it's like,
We serious?
the person at college was already told me to just like memorize the equation.
Yeah, he's right. I mean, because it's
I've been getting like 600s on the practice test. So.
okay. So what do you got here? Which of these configurations gives v equals 0 at all points on the x-axis?
On the x-axis. Wait.
One is, yeah, it's one.
All points of the x-axis. Yeah.
Oh, become wait.
All points of the x-axis. Well, because all points of the x-axis on number 1, the 2, and the negative 2 are going to be equal to some, then with the 1 are going to be.
Yeah, exactly. Whereas, like for instance, you see this diagonal.
Yeah.
If you put a point here, it's closer to this than that. So it's definitely 1. All right, which ones give you v equals 0 on the y-axis?
Well, it says y.
It says Y, but it doesn't show it.
It doesn't show the y-axis. You know where it is.
You know what the y
We're just gonna assume it's going to the x-axis.
Yeah, right in the middle. 3, yeah. So you guys actually have a pretty good... All right, so which 2 points have the same potential?
The ones
I'm gonna say any.
That's what I think. But...
No, but
Yeah.
they're on the same circle. No.
Oh,
Totally.
I can't even see the circle. That's why.
Oh.
Okay, yeah.
I was gonna say, you know, how can you tell for sure if there's no like line?
Nice. Yeah, so you guys know what you're doing.
How you think?
No, you're in good shape. You have it conceptually. Which requires the most work to move a positive charge from P to points 1, 2, 3, or 4?
the most.
No.
Yeah, it's gonna be.
No, 3.
It would be.
No. Would it be one?
Well, I'm thinking.
Well,
one.
because if you look at the cosine, they're working in the direction of the field.
So what are you working against?
You're working against the field.
You're working against the field. So
No, it's not gonna be 4.
you know it's not going to be 4. That's right.
It's not 5.
Well, I think it might have to be. What do you think? I'm trying to think of go ahead. Like, if it be constantly pushing it this way.
We'll think, when does the dot product, work is at the end of the day a dot product. When is the dot product going to be maximized?
When the cosine is.
Yeah, that's right. So when
So 1.
1 is correct, yeah.
Wait, there's no answer for this one. Like before. Oh my god.
All right. Which requires 0 work?
4.
You're all wrong. It's 3. That's right. It requires no work to move it along this path. It requires negative work to move it to point 4. Because what does that mean? Think about what that means, to move it to point 4.
You're pulling it with the field?
So the field's this way, right? What does the field want to do to this particle? Push it away, right? So in order to move it to 4, meaning start at rest, end at rest, you're pushing against the field. So it requires...
No, because you're trying to get it forward more.
So for...
You're basically acting as friction. You're just retarding.
For one,
You gotta be strong.
here's this point particle, right? Where does it want to go? It wants to go, the point particle wants to go this way. So I would have to push 1.
It would just be creative magnitude. You need to push greater than the force, then you need to stop until it's at equilibrium at 1. And for 4, you don't need to do anything, and then you need to do a force to put it at equilibrium.
To put it at.
To stop it, basically. So
But you're asking...
You need to do is stop it, and for 1, you can do it and then stop it.
Yeah. So like, yeah, you would let it go, and then you would say, whoa, 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 whoa. But you're asking the right question, because you made me force myself to think. Well, we're done. So now, yeah, right. No, because sometimes you're coming up with, like when you're in my shoes, you come up with a physical explanation to something on the spot. And usually it's just like when you guys take an exam, right? You give your best, you try to formulate the best possible reasonable explanation to answer a question. But that doesn't necessarily mean you really thought it all completely through. And sometimes with the more deeper phenomenon, it's not so trivial. So talking about stuff that's not so trivial, I want to go to, this is the last piece.
Let's put it aside, though. Remember with the wheels and friction?
Yeah.
Are you still thinking about that?
Oh yeah. I mean, you're talking about why does a wheel...
Does the force of friction from the ground act on a wheel like constant velocity?
And the answer is no, it does not. In theory. In reality, what's happening is it's deforming the body. And it's that deformation. It's not like a wheel is not a perfectly, what is it called, object. Like, it's not perfectly cylindrical, it's not perfectly inelastic. It deforms. Since it deforms around the surface, static friction acts on it. So, I was having some of it with butter. You know, it was very good. I had the butter prepared. I took the bread knife, and I went right over my finger. And I was like, oh. So I'll have some human finger with butter. No, it was a tiny cut. You know, it was very salty. I was just like, God damn it. And so I immediately ran to the bathroom. And it's not a terrible cut, but it's still, like, it needs to be covered. Yeah. So, here's a question. Here's the question of the day. Well, now, conductors, or conducting surfaces. What are things that we know about them? Well, I gave you a list of properties. So therefore, the net charge distribution is 0 inside a conductor. Right? What else? What else is the charge? And what are the other two properties?
Charge resides on the surface.
Charge resides on the surface. Well, that's the surface is at an equal potential. Why? Why is the surface at an equipotential? If the surface wasn't at an equipotential, what would the charges do?
They wouldn't be on the surface. No, they'd be inside it too, right?
Well, let's suppose that you had 2 points on the surface, VA and VB. And VA was not equal to VB. What would happen to a charge? It would move. And then what would happen? That's right. In other words, the charge configuration is going to readjust itself in such a way that what happens? It eliminates whatever that potential difference is. And similarly, let's suppose that you have a solid conductor. So let's say a metal ball. And there was a potential difference inside this metal ball to the outside surface. What would happen?
The electrons would come inside. Well, not the electrons, the particles.
Well, since, let's think this through for a second. If this existed, what would be the consequence? There would be a field, right? Let's suppose VB was greater than VA. So where's the direction of the field? It would be directed inward. But wait a second. What do we know about conductors? That the charges are going to do what? Rearrange themselves such that if there is a field, it goes away. So therefore, if you have a conductor, the potential has to be the same everywhere inside the meat of a conductor, no matter what. No, it gets weirder. Because now, watch this. What I'm going to do is I'm going to carve out a cavity inside of a conductor. So here is a conductor, make it spherical, right? And now I'm going to go take my shovel, go inside, carve out a cavity. And then what am I going to do? I'm going to put a charge inside the cavity. What happens? So in other words, this will induce a charge where? On this inner surface in such a way that what happens? In the zero field where? On the meat of the conductor. So in other words, there's going to be a field inside here. E is not zero inside the cavity.
Would there still be a positive charge on the outer surface?
Think about this. This is really amazing. So now the question is, what would you observe from this conductor?
Like the outside would become positive.
And what value? Let me make this positive Q. And let me say that this is negative sigma.
It'd be the difference between the magnitudes of positive Q and negative.
Be careful. What? And make this positive capital Q. So there would be some surface accumulation on the inner surface of negative charge. The electrons would gather on this inner surface in such a way such that what happens? There's no field inside the meat of the cavity. And then if you're observing it from the outside, what would you observe? That the outside surface would have plus Q. Now, do you understand what it...
Wait, oh, the same magnitude?
the same magnitude as the charge that you placed inside this cavity. Why? Where did these electrons come from? That's right. And so that's why what?
That's why a metal lattice makes sense, because it's like a full electron. It's like the poles of it can be restricted anywhere it wants, and it can neutralize anything, any charge given.
That's right. This is why when a thunderstorm comes, what do? Everyone needs to go out to Home Depot, buy a metal trash can, right? And just sit in it. All right? Just make sure it's grounded. You're fine.
Are you serious?
Yeah.
If it's on the ground, you're fine.
You're fine. In fact, you want to go outside. All right? You want to go outside just to make sure you're grounded. So what's happening? You're in a conductor.
I feel like my mom would get mad.
I mean, right? You're like, this is why, like, every once in a while you'll hear a news story like a car got struck by lightning, right? But they think it's like the most terrifying thing in the world. And the reality is, it's not that bad. It's not that bad of a. It's not the safest place to be because it's not a perfect Faraday cage. It's called a Faraday cage. So it's not a perfect Faraday cage, but it's a pretty damn good one. Yes.
But isn't the car off the ground
Even if you're off the ground, it may not necessarily matter because as long as you're enclosed within this conductor, it's not. It's good. The whole entire charge is going to reside on the surface.
Wait, are you supposed to, with this garbage can, you close the lid over your head, or does it not matter?
No, you probably should close the lid.
What should happen when you set these garbage cans? If you don't close, so like if lightning strikes.
The charge is going to reside entirely on the outside surface of the conductor, and there's no charge inside the surface. Yes.
What happens if you discharge that charged surface? Would you have the same shock as the thunderstorm, something like 70,000 volts?
Yeah, I mean, you can, for instance, a capacitor, and this is actually, I'm going to stray away from doing any real capacitor demonstrations because they're so potentially deadly. So we're going to go, that's the next unit. The Windshurst charges up those Leyden jars. Those Leyden jars are capacitors. And really all capacitor is basically a means of building up charge. And generally the way it's done is shockingly crude. I mean, like when you see how easy, it's so easy to build something that is so incredibly deadly. I mean, all you need is basically a bucket, salt, and water. But I'm giving you a warning. Do not do this at home.
So you can kill someone with water, salt, and a bucket?
Pretty much, yeah, and just a bunch of wiring, yeah. If you had a Van de Graaff or some type of charging mechanism.
So Zach, all you need to do is like send a bathtub with a Van de Graaff. Or the Windshurst and just start.
No. There's a specific configuration. There's a specific configuration that you need to do with the metal. Yeah, some type of wires. Yeah.
And then you just have those buckets around, and it just basically becomes a capacitor.
It becomes an enormous capacitor, and.
Oh, I know that. I have seen that example.
Yeah, I'll show you guys a couple of videos, but I'm going to tell you right now, like, don't play games with capacitors until you have a lot of experience. And just to give you an idea, I don't feel like I'm experienced enough to begin playing with them. No.
No, my father showed me one before.
Like his father is experienced enough to play with him.
Did you bring your father in so PhD? He got PhD in electrical engineering.
Yeah. So his father definitely, and since it's in electrical engineering, that means he's actually really on the hands-on side instead of the theoretical side, because you put this stuff in the hands of a theorist and he'll just die. What's up?
So wait, can we see if we want that day the master theory exactly claim with the bad?
I would say no, only because we do not have the laboratory safety setup that would be required for a high voltage experiment.
You need something like, I don't know, like I've been to my father's laboratory before that was in South Korea, but his lab was filled with these equipments, these giant equipments that actually produce voltage up to 50,000 volts.
Yeah, well, the voltage is not necessarily a big issue because that generates voltages of.
Yeah, but it's just the control mechanism itself is expensive.
Yeah.
I have a question, Mr. Bloom. So the conductor thing, this is gonna sound really stupid, but you know the Sorcerer Apprentice movie?
Don't know.
Yeah.
I know what you're talking about.
Yeah, I know what you're talking about.
Where they like he
Yeah, the
sat in
giant
like
big,
yeah,
big, big cassette.
where like they sat in the metal thing and had like the light.
Yeah, it's a Faraday cage. Yeah.
And they played like that song.
That's exactly it. That's exactly what it is. It's called a Faraday's cage. So now, the question is, if this was a sphere, how would the charges arrange themselves? Why?
Because since the electrons have gone to its cavity, you would have to equally distribute it out so that it doesn't really, it's basically became a uniform electrical thing.
All right, so let me kind of get what Hammond's getting at here. So it's uniformly distributed. Let's suppose I have some mechanism. So now I put that charge there inside this conductor, okay? And it takes on all these electrons, right? And then I have some mechanism to actually strip off all the positive charge off the surface. And I were to actually go and then proceed to add them in one by one. What would happen?
They would try to maximize the distance.
Correct. Why? Because what would they feel from this? Nothing. The inside field is zero. They'd feel nothing, so the only forces they would feel is mutual repulsion from each other. And so they would all reside equidistant from the surface or rearrange themselves in such a way that they're uniformly spread out over a sphere. Is this going to be true for other geometric configurations, yes or no?
As far as equidistant.
And that's correct. It's not going to be the same. If you went and took a square, or excuse me, a cube, a square. If you took a cube, they're not going to spread out uniformly over the cube.
Aren't they still going to try to maximize the distance though?
They're going to try to maximize any, like, I guess really,
Wait, is that because they're not all equally distant?
it's not necessarily that they're going to maximize the distance.
But the thing is like
If you guys ever have a chance to study what's called Lagrangian mechanics, which is a different reformulation of Newtonian mechanics, it's based on the idea of least principles. And basically, and you probably heard this in your chem class, systems work in ways to minimize the total energy. And so they're going to go into a configuration that minimizes that total energy. I think that's basically it, guys. That is it. Now, yeah, that's it for the unit. Now it's a matter of problem solving.
I'm still kind of confused with one thing.
Shoot.
If you have like two point particles, isn't there only like one, like a positive and a negative? Isn't there only like one spot
Yeah, but remember that's only going to be true for. Oh, I didn't do dipoles. I didn't do dipoles. I should probably do dipoles.
So, like, I'm just thinking, like, how at every distance can you get the electric field zero?
Because they're going to rearrange themselves. Be careful. It's only going to be true for certain types of configurations. Like, for instance, you have a dipole. Nowhere is the electric field going to be zero in a dipole on a line. Yes?
You had a question on that.
Yep.
What is the like rule that makes it want to have the electric field zero and stuff?
It is that the charges are going, because they are free to move inside of a conducting material, they're going to, how are they going to move in that electric field if an electric field's present? Let's suppose an electric field's present inside of a conducting material. How are the individual atoms going to behave inside this material? How? Who's going to move? The electrons are free to move. Well, actually, everyone's free to move. The electrons move. Why?
Because they have smaller mass.
Because they have much less mass. So their acceleration is going to be 1,800 times that of whatever the ion is. So what's going to end up happening? Where's the electron going to move to? The electrons are going to pile up here. And this is inside this material. And the ions are going to positive ions are going to pile up here. But what is that going to do? It's going to induce a field in the opposite direction in the material. In such a way, it's going to continue happening until that field cancels out the external field. So it's very, very clever. I mean, it's kind of, this is why I think when I told you guys last year, why E&M is so cool is because it's its own different way of thinking. Like, you're really thinking about real materials. Like, you're no longer thinking of everything in terms of a particle or in terms of a potato object or a box. Like, now, this particle has flavor to it. Huh?
This is like what everything is built on.
But yeah, this is really the foundation. This is the foundation of all chemistry.
Well, I mean, technically, you can draw all physics from this substance.
No, you can't draw all physics. Like, for instance, gravitation's separate. It's a separate fundamental force. All right. So, dipole. Dipole. Need to lay this out. So first, let's actually look at the potential due to a dipole. Do we? In which case, we're going to have to do this another time.